I'm here Sampaco from Room 20, and I am here to demonstrate how to solve problems regarding equations of motions using normal and tangential coordinates. So, in this video, I am going to solve problem 13-82 from Hibbeler's Dynamics. And the problem goes this way.
Determine the maximum speed the 1.5 megagram car can have and still remain in contact with the road when it passes point A. If the car maintains this speed, what is the normal reaction of the road on it when it passes point B? Neglect the size of the car.
Before we solve the problem, let us first summarize the procedure for the application of equation of motion using normal and tangential coordinates.
First, use normal and tangential coordinates when the particle is moving along a known curve path. Next, establish the normal and tangential coordinates system of the particle. Third, draw the free body and kinetic diagram of the particle. The normal acceleration always acts inward the positive direction. The tangential acceleration may act on either the positive or negative tangential direction. Then, apply the equations of motion in the scalar form and solve the derived equations for the unknowns. Take note that it may be necessary to employ kinematic relations.
Now, let us draw the free body diagram of the external forces acting on the car.
Based on the given figure, the normal acceleration must be directed towards the center of the curvature of the road, that is the positive normal axis. And of course, the direction of the tangential acceleration must be directed towards the direction of the motion of the car. We also have the weight of the car, equivalent to the mass times the acceleration due to gravity, and theta as the angle it makes with respect to the normal axis.
So, we are asked to find the maximum speed of the car as it passes point A and still in contact with the road. We are given here the mass of the car as equal to 1,500 kg, and the equation of the curved path as equal to y is equal to 25 minus 1 over 200x squared. And of course, the horizontal distance from point A to B, which is 25 meters. From the equations of motion, we have summation of forces along the normal coordinate is equal to the mass of the car times the normal acceleration, wherein our normal acceleration is equal to the square of the velocity of the car over the radius of curvature. Now, referring to the figure, the forces along the normal coordinate is the weight of the car times cosine theta and the normal force. And it is equal to the mass times the normal acceleration, which is v squared over rho. Substituting the given values, our weight is 1,500 kilogram times the acceleration due to the gravity, which is 9.81, times cosine theta minus normal force equal to the mass, which is 1,500 kilograms times the velocity squared over rho. Then we have this equation. Normal force is equal to 14,715 cosine theta minus 1,500 v squared over rho. Okay, so to find the velocity of the car at point A, we first determine the angle theta at point A and point B. Looking at the illustration geometrically, the slope of the curved path at any point is defined as the first derivative of the equation, and it is equal to dy over dx the first derivative with respect to x is negative 0.01 x, and the second derivative of the equation is negative 0.01. Therefore, at any point, angle theta is equal to the arctangent of the slope. And dy over dx is equal to negative 0.01x. Then we have this equation. Angle theta is equal to arctangent negative 0.01x. Now, at point A, x is equal to 0. Then, therefore, angle theta at point A is equal to 0. At point B, x is equal to 25. Substituting 25 to our equation, we have theta is equal to arctangent of negative 0.01 times 25. Calculating our equation, then we have angle theta at point B is equal to 14.04 degrees. Next, we determine the radius of curvature at point A and at point B. We have the equation for the radius of curvature as 1 plus the square of dy over dx over quantity into the 3 halves over the absolute value of the second derivative of the equation. For the point A, our x is equal to 0. And therefore, given this value, we have the radius of curvature at point A as 1 plus negative 0.01 times 0 squared to the 3 halves over 0.01. Then we get 100 meters. For the point B, we have x as equal to 25. Then, given this data, we can get the value of the radius of curvature at point B as 1 plus 0.25 squared to the 3 halves over 0.01. Therefore, our radius of curvature at point B is 109.52 meters. Now, since the car is required to just about lose contact at point A, then we assume that our normal force at point A is equal to 0. Then, using these values, we substitute it to our first equation, then we get 0 is equal to 14,715 cosine 0 degree minus 1,500 v squared over 100 meters. Then, solving for our velocity, we have 31.3 meters per second. Okay, so to find normal force at point B, we use this equation and substitute these values to this equation. Since the car is moving from point A to point B at a constant speed, which is equal to 31.3 meters per second. Then we get NB is equal to 14,715 cosine 14.04 degree minus 1,500, the velocity of the car, which is 31.3 square over the radius of curvature at point B, which is 109.52 meters. Then, calculate, we get 840 newtons as our normal force at point B. So, the problem is solved.